in this video, we're going to talk a little bit about force and potential energy. You already know a little bit about how these two things are related. So the change in potential energy is equal to the internal work that's done. In fact, it's actually the negative internal work, and we define it that way, as we said in one of the previous videos. When we go to calculate that internal work, what we're doing is we're taking the integral of the force over the displacement of the object. So one thing I want to do to think about how we might connect these in a different way is to think about taking a very small displacement. And so calculating the small change in potential energy that's a result of taking a very small displacement. So basically, we take away this idea of the integral, and we just add up a little bit. Now, physicists do this all the time. We take these little bits and we add them up, and we think about these as numbers that we can move around. And mathematicians would be really upset if they knew we did this. Actually, maybe they do know we do this. Point being, this helps us to make an argument for what the force is in terms of the displacement. I'm sorry, in terms of the change in potential energy. So we're going to do this in one dimension. So we'll ask, what's the small change in potential energy that arises due to a force in the x direction and a displacement in the x direction? Now we'll move this displacement over to the other side, and we'll find that the spatial derivative of the potential energy is equal to minus the force component in the x direction. So in fact, what we have is a relationship between the force in the x direction and the spatial derivative of the potential energy. It's negative the derivative in this coordinate direction. We can go into a lot more detail about this, but the upshot here is that if you want to calculate the force, the vector force, you would take the gradient of the potential energy. That's going to give you each of the components. So if you haven't seen that gradient operator before, let's unpack that just a little bit. So if I were going to take the gradient of the potential energy, what I'm going to do is I'm going to take the x derivative, multiply that by x hat. I'll take the y derivative, multiply that by y hat, and take the z derivative and multiply that by z hat. So this would give me the force on the object in each direction. So the negative of this, the negative gradient of this, oops, missed the negative sign out here. The negatives on all these give me the components of the force in each direction, fx, fy, and fz. So this is actually a really useful way of thinking about the potential energy, particularly when you have a graph of the potential energy. For example, let's take the situation where we have some hill and we're mapping out the gravitational potential energy, and it kind of looks like that. So here's the potential energy as a function of distance. So the thing that we can see immediately is that if this is a graph of the potential energy as a function of distance, when the derivative of the potential energy, the spatial derivative, goes to 0, that implies that the force in the x direction goes to 0. This implies something about what we will call equilibrium points. So wherever the slope of the potential energy function goes to 0, we have equilibrium points, so at these different peaks. Now, one other thing that's quite interesting is to investigate the stability of those points by thinking about putting a little ball at each of those locations and giving it a push. Now, clearly at this location, which we'll call B, if we give the ball a little push, it's going to come back and sort of roll around here. This would be a stable equilibrium. Whereas A and C are unstable, because if we give the ball a little push, it's going to run away from those locations. So while the first derivative tells us about where these equilibrium points are, the concavity, or the second derivative of the potential energy function, tells us about whether it's stable or unstable. So when thinking about these graphs, it's a very useful tool, this idea of connecting the force to the spatial derivative of the potential energy. It's a useful tool for thinking about stability of points. One final thing to note is when you have one of these graphs, you can think about what the kinetic energy of that system is if you know something about the total energy. So we'll draw another one of these graphs. So it looks like this. So let's say the system has a total energy given by this dotted line. So this total energy is the sum of the kinetic and the potential energy. Well, at every point, we can measure what the potential energy is. Right? So there it is there it is there, and so forth. And what we find is that if the sum of the kinetic and potential energy is a constant, that is, there's no external work done, then the kinetic energy of the system is precisely given by the arrows that go from the potential energy curve to sort of the dotted line, the limit of the total energy. So these are the kinetic energy values at each of these locations. One other thing you notice is that if there's a particle that exists, say on this hill, and it has this total energy given by this dotted line, it cannot go past this point. Because once it goes past this point, the potential energy that it would have, the potential energy that the system has is higher than the total energy that the system has altogether. You can't have negative kinetic energy, and so the object cannot go past this point. It doesn't, the system doesn't have enough energy for the object to get that far up. So that's how you connect force and potential energy. It's also a way of thinking about graphs and how you can get information about kinetic energy from potential energy graphs.